Welcome back to video 2, when we're still talking about periodic properties of elements. And the first periodic property we're going to be talking about is atomic radius, or atomic size. And just to give you an idea, this is actually hard because this is actually not particularly easy to define. And that's because the electrons are the outer part of an atom, so they would define the outermost boundary and by extension its size, but we can never actually pinpoint them to a particular position. And the other idea is that the probability of finding an electron doesn't actually hit zero at some distance. Actually, it approaches zero as you get an infinite distance away from the nucleus, although it does drop to some very, very small values very fast. So when you look at these pictures of atoms, what those actually are is people have basically drawn the shape that contains either like 95 or 99% of the probability of finding an electron in that region of space. But technically, they're the size of the universe. So there isn't really a convenient boundary. So what we do is we make something up. And it turns out that because of their much greater mass, protons, and by extension entire nuclei, are far less wavy than the electrons are. And they can be pinpointed in space with very high precision. So we determine the radius of an atom by determining the position of adjacent nuclei, like in this figure here. And we just split the distance. So on some random metal, we find that the nuclei are 286 picometers apart. So we would call the radius of those atoms half that distance, or 143 picometers. And you can do this for metals. You can do this for anything. So, for example, the bond length or the distance between the adjacent nuclei and a Cl2 molecule are not quite 200 picometers. So we could call the radius 100 picometers. But and then you could do this for a bunch of compounds, and sometimes you can get some average length. Or if you define one, you can define another. So for example, for a carbon-chlorine bond in some particular compound, we could assume 100 picometers for the chlorine. If the total distance is 177 picometers, that means that you would say that the radius of the carbon atom in this bond is 77 picometers. And what you could do is you could play this game for a whole bunch of different compounds and get an average size for chlorine or an average size for carbon. So what I want you to do next is think about how the radius of a particular element, let's focus on this picture maybe for example, how they change as you go from left to right across a row in the periodic table, and how they change from top to bottom. Now think about number 1, the physical meaning we ascribe to particularly the quantum number n. And the other thing I want you to think about is the whole notion of shielding that we talked about in the first video. And the answer to these questions is in those. So think about it, scribble down your guesses, do whatever you want to do. And here are the answers. Now, first off, we're not going to talk about these transition metals in the middle because, well, they are difficult. So these bars represent the height or the radius of a particular element, and the numbers are written down there in angstroms. Remember, an angstrom is 10 to the negative 10th meters. So what we find is clearly is that they're increasing going from right to left, which is something people often guess correctly, and they increase as you go from the top to the bottom. And I want to discuss both of these in turn. And I'm going to start with the top to bottom trend first because it's easier. So what's different about the outermost electrons as you go from the top to the bottom is simply that they've got a larger n value. And a couple lectures ago, we told you that the size of the orbitals actually increases with n. It tells you how big, or I should say electron state. I thought I'd gotten rid of that word orbital. How much bigger they get. And I will say this is a relatively large effect. And I will give you this as an example. So here is this graphic here. Shows you the average distance, or this line right here, 1s, 2s, 3s, shows you the 95% probability drop off for that particular type of electron. So a 1s electron only goes out to here. A 2s electron, which is the blue line, it has a little bit of a chance of being here. Mostly it's around here, and you're not going to find it very often beyond this line right here. A 3s electron, it has a small probability of being somewhere in this. It has a small probability of it being somewhere here. Most of the time it is somewhere in this distance away from the nucleus, and only like 1% of the time is it beyond this line. So this is the extent of a 1s type electron. This is the spatial extent of a 2s type electron. This is the spatial extent of a 3s type electron. And and this is to scale. So these outermost electrons, as you go from 1s to 2s to 3s, get progressively further out. And this would be pretty much the same if you're looking at p-type electrons or d or f or any of them. And what's happening as you go down a group? Well, basically, the outermost electrons as you go down from lithium, like for hydrogen, it's a 1s electron. For lithium, it's a 2s type electron. And for sodium, it's a 3s type electron. So that's why the atomic radius increases in quite a bit as you go from the top to the bottom of the periodic table. Now the left to right trend is a little more complicated, but not much. So here's what's going on there. So as we talked about before, the number of shielding electrons as you stick in one row is constant. But the nuclear charge is increasing, which means that by extension, the effective nuclear charge is also increasing. And then what's important here is the effect that has. As these outermost electrons feel an increasingly larger nuclear charge, they are brought in tighter. And so they're a little bit closer in. So the radii actually decrease as you go from left to right, and that's because the effective nuclear charge is increasing, and that brings them in. So that's the explanation of that trend. So to see if you have got it, answer me this. So which one is going to have a greater radius, aluminum or silicon? So look where they are in the periodic table, and know that the trend is that they actually get smaller as you go from left to right, which means that silicon is going to be the smaller of the two, which means, I got two questions here. So compare aluminum and silicon and aluminum and gallium. So aluminum versus silicon is the inter-row trend, or the intra-row trend, and aluminum and gallium is the intra-column trend. So the trend is that they get smaller as you go from left to right, which means silicon is going to be smaller, which means aluminum will have the larger radius between those two. And between aluminum and gallium, they're in the same group, so they get larger as you go down, which means in that case, gallium will have the largest one. And so the questions we would ask you on exam is to give you a certain set of elements and to compare their relative sizes, just like you did here. Next up, ionization energy, so see you at video 3.